Okay, today we are just going to be reviewing. Reminder that anything that's going to be for credit has to be turned in by 5 tonight. The final exam, see, this class meets at 9:30. So 9:30 Monday, Wednesday, Friday is right there. May 2 at 10 a.m. So right here on Monday at 10. So it'll be just like normal class almost. You just be able to come a little bit tardy from what you normally do. I want to make sure it's clear when and where the exam is. What's it going to cover? It's going to cover the entire semester. So it will have a higher emphasis on material since the last exam, but it will cover the entire semester. So I will probably have something like 1 or 2 questions per chapter up until the second exam, and then the more typical 5 per chapter after that. So it's emphasizing the later, but it's cumulative over the entire semester. Approximately half, again, are going to be questions that you guys wrote, and half will be coming from the textbook's test question database. And you'll have 2 hours to complete it. All you'll need to bring is your pencil and calculator. Remember, calculator, not cell phone. Okay, one question that you know is going to be there, the scientific method. Sadly, last Friday, when I was at the Nebraska Academy of Sciences, I thought up a beautiful question to ask you for this question, because I give you a scenario, and now I can't remember what it was. Now I have to sit down and think some more. But I know it was beautiful. I was like, oh, that's going to be perfect.
And then you forget.
Yes. Okay, so what you have to do on that question, just to make sure it's real clear to everyone, is you're going to have 1, 2, 3, 4, and you essentially have to write what's on this page with the 1, 2, 3, 4. So step 1, observe something interesting. Step 2, create a hypothesis that explains why the observation occurred, is based on scientific ideas, and makes predictions that can be tested. Step 3, create a test and do that test that tests a prediction of the hypothesis. Very important to remember, you're not creating a test to recreate the original observation or see if the original observation was correct. You're creating a test that will test a prediction of the hypothesis. And then step 4 is a branching statement. Step 4, if your experiment confirms the prediction of the hypothesis, you didn't prove it right, but you failed to prove it wrong, and that's what we consider good. And so you have more confidence, but you go back and you test a new prediction or test a different way. So you continue testing. You don't just do the same experiment over and over, right? That would be redundant. That's the definition of redundant. Instead, you do tests in different ways. If it fails, that is, if your prediction turns out to be wrong, then you know your hypothesis was incorrect. And so then you go back with your added information and modify the hypothesis to make it more correct. So in this sequence, when is the scientific method complete? Never, right? That question is so fundamental, it's almost rhetorical. Never. It's never completed. So what's the purpose of the scientific method?
So you can be more sure of the answer.
So you can be more sure. Any other? You got an answer for me, Zach? I thought you... What? Okay, this is how scientific knowledge is gained. What we're doing is systematically making hypotheses, educated guesses as to what's going to happen, and then we test to see if our guess was right. And as we go through, every time we were wrong, we can rule out things. And so, in theory at least, this method should always bring you closer and closer to truth. It doesn't necessarily say you'll ever get to truth. We don't talk about it's scientifically proven, but it gets to the point where we think it would be silly to not believe it's true. Okay, and that's obviously, once again, going to be a big portion of the test grade. It'll probably be about 10% of the test grade is that one question. Now, that's half of the question. What's the other half of the question? I give you a scenario. So that is, I give you an observation like you notice that sunrise changes as you go throughout the year. Right? That's an observation of something that is reasonably interesting. And then you have to go through those 4 steps. So if I told you your observations, you notice that the sun rises at different times throughout the year, what would you write for step 1 of the application portion? Exactly that. Right? Step 1 is the observation. But I have you write it out to make sure that you've internalized that and understand, yeah, that observation was the first step. So it's not a trick thing. It's just there to make sure that you understand, yes, when I apply it, that's my observation. It doesn't have to be verbatim. Some people write it verbatim. Some people abbreviate. It's fine either way. As long as it's clear that what you're stating for your observation is a fair facsimile of what I had stated. For step 2, a hypothesis. You got to create a hypothesis. What kind of hypothesis would you come up with for that? You're tired of looking away from me. What kind of hypothesis would you come up with?
The world is not a sphere, it is an oblong shape that as it rotates, it kind of gives its weird light.
Okay? The Earth is not spherical in shape, but is oblong. Okay? Now we know that's not the correct answer, but that's fine. You don't have to come up with the correct one. You need to come up with one that could explain why you would have sunset at different times. Then, once we have the hypothesis, what's the next step? Find a way to test it. So you have to describe a way to test it. What would you not do for this test? Let's go with the obvious thing that you would not do. Okay, maybe it's not the obvious thing since everybody didn't blurt it out. The obvious thing you would not do is to get up every morning and record the time the sun rises. Why would that not be the test of his hypothesis? Well, recording data is good, but that was just the observation, right? Doing the observation is not going to be testing the hypothesis to explain why the observation occurred. That's just coming back and saying, yeah, I did observe it. Right? It's just confirming your observation. So for your test, if your hypothesis is that the Earth is oblong, there's a pretty obvious test. Do what? Okay, take pictures from space. We have to come up with a way to do that. The flat Earth people believe that we've never actually taken a picture from space of the Earth. They think that I saw this thing. NASA takes composite pictures. They take like 10 pictures and stitch them together so they have higher resolution. And these people say, oh, that's just an artist's rendering. They're just saying this is what we think it looks like. They don't know what it really looks like. Anyway, but yes, we now have things that orbit the Earth, and we can take pictures from space. And so take a picture at this point in the orbit and this point in the orbit, and we can get the dimensions and say, is it spherical or not? Now we get to step 4. What outcome would confirm your test? Or confirm, your hypothesis. Okay, so if you find that the dimensions are different, then it's a confirmation. And what would you do? So you write down here, you would say, if dimensions are similar, so it's not oblong, then what?
Then it supports it, so then you make a new test.
Yeah, then test a new prediction or a new way. So that's go back to step 3. But I have to write out the words. This outcome, I'll do this. Outcome that fails, if it's spherical, if I find out, hey, all the dimensions are the same, then I know that my hypothesis was wrong. then I have to go back and create a new hypothesis because now I know, okay, that wasn't the answer. So I have improved my knowledge because I've removed a potential answer. Okay, so that's like 10% of the test, why I spent so much time on it. That's the one part where we know what I'm talking about is going to be on the test and helpful to you. Any questions about scientific method? Y'all understand why it's so important here, right? If you don't understand the scientific method, you have no reason to have any kind of confidence in scientific information, right? Other than the old appeal to authority. Well, these guys are scientists and they say it's true, so it must be. Right? Understanding the method helps you to have more of a realistic reason to have confidence and to know how much confidence you can and can't have. You can't say just because it's the scientific answer, it's the correct answer. It's what we believe to be correct by experimentation, but it could still be wrong. Okay. I've already gone through both of my scientific things. Chapter 1 was just defining physics, knowing what we do in physics. At this point, we've studied mechanics. What's mechanics? It's broken up into two areas, statics and dynamics. It's basically the study of how objects interact. Statics is just looking at forces pushing on things. Dynamics is how things respond, what makes them move. Thermodynamics, what are you studying in thermodynamics? Okay, you're studying heat. I should write here. Mechanics is, hey, I saw you got them all graded. Thanks. So here are your lab books for those of you who want them. Yeah, I'll just leave them here. I'm not going to worry about spreading it. Okay, thermodynamics was heat and temperature things. My choice of color here is not good. There's a better choice of color. Electricity and magnetism, well, I think that's pretty clear, right? I don't think I need to put a descriptor on that. Optics, it's probably clear, but just to make sure. Optics, you're studying light waves. Atomic physics, nuclear physics, particle physics, condensed matter physics, we didn't talk about those things. These things down here are more advanced topics. Atomic physics is talking about, of course, what makes up an atom and why we have stable atoms. It's what leads you to the field of physics. Nuclear physics is talking about what's going on inside of the nucleus. If you look at that nuclear science poster back there, that's what it's about. Particle physics is more fundamental. Particle physics is talking about what is the stuff that makes up everything. What is a proton made up of? Protons are not elementary particles. You can break them up into smaller pieces. Well, they are made of smaller pieces. You can't break them up. A proton is an up, down. It's two up quarks and a down quark. You can't separate. You can't pull away an up quark. But you can have a particle interaction where you destroy the up quark and create something else. So that's what particle physics is looking at. So you talk about quarks and you talk about leptons. Electrons or leptons, they are fundamental. Electrons are not comprised of anything. They're fundamental. And then condensed matter physics. Put that on there because that's what my PhD is in. So just some different fields. Obviously, you don't have to know about condensed matter physics. We also have to know about units. And we have the International System of Units, the SI system. Obviously, SI is not international system. It's Système International because it's in French. And so you should know what mass is measuring, amount of material present. Its unit's kilogram. Of course, we know what time is measuring. Its unit is second, not hours or minutes. The fundamental unit is the second. Hours and minutes are derived from the second. Forces, the first thing that you didn't necessarily, well, mass, you may not have necessarily understood what mass was. But force, you definitely didn't necessarily have to understand that when you started this class. Force is something that's pushing or pulling, and it has units of kilograms times meters per second squared. Pretty complex unit. The Newton itself is an abbreviation for the more complex units, so we don't have to write kilogram meters per second squared all over the place. Similarly, energy, which now you should have a clear distinction between energy and force. Energy has units of kilogram meters squared per second squared, which is a Newton meter, and we give it its own name, the joule. Then speed, meters per second, acceleration, meters per second squared. Make sure you're real clear on the difference between acceleration and speed. Right? That's something that students almost always come into class with confusion about. Largely because you know in your car you have the accelerator. And you press on the accelerator, you go faster, and people start to equate fast with accelerate. But what does accelerate actually mean? Change in speed per time. And so the units are the units of speed divided by time. That's why you have meters per second squared. Then we have some of the more obscure ones. Momentum, kilograms times meters per second. Angular momentum, kilogram meters squared per second. Torque, Newton times meter. Notice, Newton times meter here, Newton times meter here. But torque is not the same as energy. What was the difference in torque compared to energy? Work was force times distance. There's another word. Force times the distance parallel to the force. You have something moving parallel to the force, then you have work done. And so that's where we get the unit of energy. Torque is force times distance perpendicular. There's no motion necessary for the torque. For the work, you have a force and you have motion. It's a delta x. For the torque, it's force times the lever arm, a length, not a changing distance. So they're fundamentally different things, even though their units turn out to be the same. Angular momentum. What's a rad? It's a radian. Now, if we had done nuclear physics, we would have also had a rad as a rad. So we have that unit with two different meanings. But it's a radian. It is the natural unit for angle. There are 2 pi radians in a circle, and there's no units to radians. So they mysteriously vanish because they actually are a way of saying we measured an angle and we measured in the correct unitless unit rather than using something like degrees. Degrees, well, then you're going to have to use a conversion to get it to radians. Hence the radians versus degree for angle. Finally, angular acceleration, the rate at which angle is changing. Angular velocity is angle per time. Angular acceleration is angle per time changing per time. So how quick something's rotating faster. And moment of inertia. What is moment of inertia equivalent to for linear motion? So what? Not acceleration. Mass. It's the rotational equivalent for mass. But unlike mass, you can easily change your moment of inertia. You put your arms out, the mass is farther away, and for rotational purposes, it's like you have a bigger mass. You have a bigger inertia to keep you from changing your rotational state. Remember, mass and inertia are really the same thing. That is, mass is how we measure inertia. Okay, now we're ready to get to chapter 2. Oh yeah, we're actually not doing as bad in time as I thought we were. So chapter 2, we start talking about motion. So we had to know the difference in distance versus displacement. That is, displacement is the difference between starting and ending point. Distance is how much ground you traveled. So if I do a complete lap and come back to my starting point, my distance would be the distance of the track. My displacement would be 0 because the difference in ending and starting points are 0. Likewise, what's the difference in speed and velocity? This one I'm pretty sure you all know. Velocity has direction with it. It's a vector. Speed is just how fast you're going. Velocity is how fast you're going and the direction. So make sure you understand the distinctions between vectors and scalars. Kinematic equations. You'll be given the kinematic equations. Remember those kinematic equations were things like x is equal to x initial plus v initial t plus 1/2 a t squared Right? You'll be given the equations, but you need to know what they mean and how to use them. So you need to say, x is the position. So x initial is the initial position. T is the time, v is the speed, a is the acceleration, and be able to put numbers in. That's just one of the kinematic equations, but make sure you understand how to use all of them. So you can calculate things like how long it should take a ball to drop 1 meter, like we did in our very first lab. Right? We didn't do the calculation, we dropped the ball. Not in the figurative sense, but in the literal sense. And you should be able to now calculate how long it should take. You should be able to take a problem like, some basketball player jumps up, dunks the ball, and lands, 1.5 seconds later. How high did he jump? You should be able to do that calculation because you just have an equation like this. X initial and X final are the same if he landed on the ground. You have the time. From this you'd find the initial speed, and then with the initial speed, go back again. You could find it shorter other ways. All right, chapter 3, falling objects and projectile motion. Now, I was talking a little bit about projectile motion when I'm talking about the jumping of a basketball player, but I didn't get specific. When a basketball player jumps, he usually isn't jumping straight up. He's jumping horizontally and up. What is his acceleration going to be in the horizontal direction? Jump up in the air, go up for the big dunk. He's moving horizontally. How is his velocity horizontally changing? It's not. Assuming there's no air resistance. Remember, we assume no air resistance unless we're told to consider it. What about his vertical velocity? He was going up. He slows down. At his highest point, what's his vertical velocity going to be? 0. Then what happens? Comes back down. So what was going on with his acceleration during the jump? What was the acceleration direction when he was going up? Down. Well, how could he be going up and have a downward acceleration? What does that mean? Yeah, he's slowing down. If the acceleration is the opposite direction from the velocity, you're just slowing down. It's perfectly possible. Coming down, he was speeding up, downward. So what direction was the acceleration? Downward, because he was speeding up downward. So the velocity acceleration was the same. What about at the apex? At his highest point, what was his vertical acceleration? It's still g downward. Still g downward. I didn't think that was what you said. If that's what you said, well, I shook my head wrong. It's g downward, which makes him not float, but come back down. If the acceleration at the top was 0, then his vertical velocity would have stayed the same. So it would have just floated. Right? So the fact that he came back down meant his acceleration couldn't have been 0. And it was still down because he came back down, didn't go up. So we have what we call independence of motion, that the vertical and horizontal directions can be treated exactly the same. So that gives you the classic physics problem. If I have 2 bullets and I put one in the gun and hold that gun perfectly horizontal and hold the other in my hand, and at the same instant I pull the trigger and drop the bullet that I have in my hand, which one hits the ground first? What'd you say? Yes, if there's no air and if the earth is perfectly flat, right, we have to put in these kind of contrived situations, then they'll hit the ground at the same time because they have the same downward acceleration and they have the same initial downward velocity. They were both not traveling downward. When I fired the gun, the bullet was going horizontal, right? No downward motion. And so they would fall and hit the ground at the same time. Of course, the one that came out of the gun had a really big horizontal velocity, so it's going to be way over there when it hits the ground. Of course, assuming there's no wall, no people, no cars, right? Perfectly flat. The other one's just right here because of the horizontal velocities. Okay. We're ready to move on to chapter 4 already. Yeah. Newton's laws. Super, super important for physics. When you're talking about mechanics, you're in the realm of Newton. Newton did his 3 laws. The first law, the law of inertia, says that an object will stay in constant motion. That means constant velocity, unless a force acts on it to change it. The second law just puts that into an equation that says the net force equals ma. Notice I put an arrow over the force and an arrow over the a because those are vectors. They have direction with them. And it's net force is equal to ma, not force equals ma. Right? Force equals ma is wrong. If I have a force of gravity acting on me right now, but I'm not accelerating. I have to take the sum of all the forces acting on me, and then from that find what the acceleration is. Then the third law that says that if I put a force on something else, it puts a force on me. So if I hit the table hits me back with a force that's exactly the same as the force I put on it, but in the opposite direction. So if I punch the table really, really hard, which puts the bigger force, hand on table or table on hand? It is the same. So which breaks, hand or table? Why hand? Because it's weaker. Oftentimes we tend to think that the forces are different because we have different outcomes, but it's just the materials are weaker. Make sure you can identify the common forces like the normal force that's keeping you from falling through your chair, force of friction that keeps you from sliding out to the side of your chair, the force of a spring, which is force is equal to k delta x. If I put the vector signs, I have to put a negative sign because it's in the opposite direction that you stretch it. Force of gravity we had 2 versions of. The first one we learned was force of gravity is equal to mg. G is the acceleration of gravity, or the gravitational field, that by definition points down. And the normal, I already talked about the normal. Static and kinetic frictions, we have those equations. Force of static friction is less than or equal to mu static times force normal. Force of kinetic friction is equal to mu kinetic times force normal. And remember, we talked about things like why cars have anti-lock brakes. Because the maximum you can get for static friction is higher than what you get for kinetic. So the anti-lock brake is bringing the car up to just where it starts to skid, loosening up, doing it again, and keeping you very close to the maximum static friction so that you don't skid and you have a higher friction that you would have had if you had skidded. An expert driver can beat the anti-lock brakes. Most of us probably can't. All right, chapter 5, going in circles. I dusted off last year's final review presentation because, review is always going to be pretty much the same. But I did fix the word centrifugal because I had centripetal for both, and they can't both be centripetal. Make sure you know centripetal means toward the center. Centrifugal is away from the center. And if something is going in a circle, that means its direction of motion is changing. So it has a velocity that's constantly changing. What do you call it when the velocity changes? Acceleration. So to go in a circle, you have to have an acceleration that's constantly changing the velocity, changing the direction, but not the speed. If the acceleration was parallel to the velocity, it would change change the speed. So it has to be perpendicular. So for a circular motion, you have an acceleration that's toward the center, hence the word centripetal. And it turns out that centripetal acceleration is v squared over r. It's proportional to the speed squared divided by the radius. And so this explains why you can do things like have a bucket with water in it and swing around a circle and have the water not come out. When you are up here, there's acceleration of gravity that's trying to make the water come down. But you need a downward acceleration of v squared over r just to stay in the bucket. If the acceleration is less than that, it would go through the bottom of the bucket. And so as long as the centripetal acceleration is bigger than the acceleration of gravity, the water will just stay in there and the bucket will be adding an additional downward force to pull the water down. If you slow down, So AC drops, well, then the water will come out. So you got to make sure you have your speed fast enough where the water will come out. Still in chapter 5. Kepler's 3 laws. You might remember, we talked about orbits. Johannes Kepler came up with these 3 laws from pure observation. He was actually taking the data that Tycho Brahe had earlier measured, then Tycho died, and looking at that data, he came up with these 3 laws that said the Earth orbits around the sun, and the other planets orbit around the sun in elliptical orbits with the sun at one of the 2 focal points of the orbit, called, plural of focus is foci, so the sun is at one of the 2 foci. The second law was that the area swept out by a line that goes from the planet to the sun is constant in time. So when a planet is farther away from the sun, it goes slower. When it's closer to the sun, it goes faster. That was our important output of that. We didn't do calculations with it. We just said for a single planet, when it's closer to the sun, it goes faster. When it's farther away, it goes slower. And then the third law related the time it takes to do one orbit, called the period, to the average distance. That was the period squared is proportional to the semi-major axis, I'll put A here, cubed. He came up with these just by looking at the motions, the observation of where planets were in the sky. And about 100 years later, Sir Isaac Newton came up with his law of universal gravitation. So here's the second equation for the force of gravity. And based on that and his 3 laws of physics and his newly developed calculus, so he could work with these laws, he was able to derive Kepler's laws. So Kepler's laws were just based on observation, and then Newton came up with reasons why they had to be true. Now we get to actual energy chapter. So definition of work, really important. Work is force that makes an object move. Or more specifically, work that makes an object change its motion. So if I take this chair and I push it and it starts moving, I did work on it. Force times that distance it moved. If it's coming toward me and I push it and make it stop, I did work in that case as well. But since my force was the opposite direction to the distance it traveled, I did a negative work. Energy is a measurement of how much work has been done. So we actually have the net work is equal to the change in kinetic energy. Kinetic energy is energy something has because it's moving. Has energy because it has the ability to do work. So if I'm standing here, I do have a little ability to do work. That is, if I were to just relax my legs, I'd fall down, hit the ground. There'd be some work involved. We call that potential energy. I have that energy, that ability to do work because of my position. If I start running, I will also have the ability to do work because of my motion. If I run and I hit the wall, well, I won't do much work for the wall. But if I had Daisy stand up and if I ran and hit Daisy, I would do a fair amount of work to Daisy. I would apply force and I would make her move. That's doing work. And I would be able to do that because I was moving. So that's what kinetic energy is. And kinetic energy has the equation 1/2 mv squared. Once again, all these equations are given on the exam. You don't have to memorize them, but you have to be able to understand them and use them. Right? The memorization isn't important, but the understanding, that's important. So you'll need to be able to solve some simple problems having to do with work and energy. Now remember, most of your problems are not calculational. Most of them are explaining a concept or that kind of thing. Except for the scientific method, they're all going to be multiple choice, just like you've had before. Make sure you know the difference between power and work. So in a nutshell, what is power? 6 words. No nutshells because we don't have much time. I'm going to answer. Power is the rate at which work is done. So if you do work quickly, that's a high power. If you do it slowly, that's a low power. So we could take something like a car going up a hill. If it goes up the hill quickly, it used a lot of power. If it goes up the hill slowly, it used lower power. But in the end, to go from the bottom of the hill to the top of the hill required the same amount of energy. It's just the time factor. If it goes fast, then you have this big energy divided by small time and a big number. If it goes slow, you have the same big energy divided by a big number and a small power. So power is the rate of work being done. Momentum and impulse. Impulse is just a fancy word for change in momentum. I was looking at somebody's homework assignment 6. I have it now regraded. And I noted the question there that asked, what's the change in momentum of, I think it was a train. No, it was a car. I don't know, something like that. Something went from this speed to stopped. And it says, what's the change in momentum? And then the next question was, what's the impulse? Well, once you found the change in momentum, how do you answer what the impulse is? They're the same. Impulse is equal to force net multiplied by time, which is equal to change in momentum. So they're the same thing. Some people use the word impulse for the left side of this equation. Everybody uses the word change in momentum for this side of the equation. So impulse is just equal to change in momentum. Remember the symbols. P for momentum. It's not obvious. So remembering the symbols we use is probably a bigger part than most other things you have to do. So be able to solve problems, know when momentum is conserved. Is momentum conserved for my body when I run and hit the wall? Going with no. No, my body's momentum wasn't conserved. Is momentum for my body conserved if Tyler stands up and I run and bounce off of Tyler? For my body. If I run and bounce off of Tyler, is my momentum going to change? It will. So momentum won't be conserved. But if we combine my body and Tyler's body, so we look at both things that are in the collision, then the momentum will be conserved during the collision. Not before, not after, because I could be getting some energy from the ground, getting some impulse from the ground. He could be getting some impulse from the ground. But during the collision, because it's so short and the net forces exterior to us are small compared to the force between us, momentum is conserved during the collision. Now, in lab, we did a collisions lab. We had two kinds of collisions that we explored. Elastic and inelastic. If I run into Tyler, is that likely to be elastic or inelastic or somewhere in between? Let's define them. Elastic, the kinetic energy is unchanged. So no kinetic energy, no mechanical energy is lost. Inelastic, the kinetic energy is changed. Some mechanical energy goes into something else. If I run and hit Tyler, is any of my kinetic energy going to go into something else besides us moving? Yeah, it is. We're going to have things like ribs collapsing and then pushing back out. That's taking some energy away. And so we call it inelastic when you lose that kinetic energy. And all we did in this class is we said completely inelastic. They stick together. So if instead of just bouncing off of him, I tackle him, wrap him up, we stick together, then that would be a completely inelastic collision, like we did in lab when we had the two carts hit each other and stick together. Seem to be able, I think that's enough said. You need to be able to differentiate between the elastic and inelastic collisions. Rotation of solid objects. Rachel came up and sat and spun around for us when we did this, right, Rachel? And so she spun around, put her arms out, put her arms in. We observed that when she put her arms out, what happened to her rotational rate? She slowed down. She brought them in. She sped up. Why? What is she changing when she puts her arms out versus in? She's changing her moment of inertia. Momentum was mass times velocity. Angular momentum is the rotational equivalent to mass, the moment of inertia, times the rotational equivalent to velocity, the angular velocity. So when she brings her arms in, she's lowering her rotational mass. But if there's no torque acting on her, just like Newton's second law, net force is mass times acceleration, which means that change in momentum is net force times time. The change in angular momentum is net torque multiplied by time. So she was on something that let her freely spin, so the net torque was 0. So if the net torque was 0, her angular momentum had to be conserved. But if she lowered her mass, she had to raise her velocity to keep it the same, angular momentum. So that's why bringing them in, lowering her rotational inertia, required her to then spin faster to keep the same angular momentum. So make sure you understand those kinds of principles with rotation. You have your rotational variables that are, angle is equal to the arc length divided by radius. Angular velocity is equal to the tangential velocity divided by radius. Angular acceleration is equal to the tangential acceleration divided by radius. Not very difficult to remember those. They'll be given, but you need to be able to do conversions, find the angle. What units do you have if you take S's arc length? What units are you going to have for arc length divided by radius? Arc length has units of what? It's not a time. It's a length. What about radius? What is it? It's a length as well. Length divided by length is unitless. So this is no units. What do we call the units that are no units for angle? Yeah. So the natural unit there for angle is radians. Then we turned a page, got to the material for the second exam. We started talking about behavior of fluids, and we had to differentiate between fluid, liquid, and gas. What were the three common states of matter? Solid, liquid, and gas. Defined by things like a solid can't change its volume or shape because the atoms are in fixed positions. A liquid can't change its volume, but it can change its shape because the atoms are held together, but their positions can move relative to each other. A gas can change its shape and volume because the molecules are free. Well, fluids are things that flow, and both liquids and gases flow, so both of those are fluids. We also had a few bizarre things. We talked about a colloidal suspension and a plasma. Those are special cases. Colloidal suspension is usually a liquid, plasma is a gas, but they're special cases of fluids because they still flow. Pressure, we talked about pressure, the force per unit area. Things like if I stand on a 1 square inch block and your finger's underneath it, it will hurt a lot more than if Daisy stands on that same 1 inch block and your finger's underneath it, because we have the same area, but my force is much bigger than hers. And so the pressure, the force divided by area, is going to be much bigger from me. It's going to hurt you a lot more. So make sure you know what pressure is. Understand where atmospheric pressure comes from, the weight of the molecules above us. Buoyancy, that buoyancy principle, which is, less dense things float up. Archimedes' principle that says the weight of the displaced fluid is equal to the weight of the object that displaced it, if it's floating. If it's sinking, the volume of the displaced fluid is equal to the volume of the object that's sunk. So make sure you have Archimedes' principle and can understand how things float. And finally, we have that Bernoulli relation here. Bernoulli relation, the faster a fluid is passing, the lower the pressure. We didn't get a chance to see this past week, but other parts of the state, like Omaha, did have tornadoes. Tornadoes, in essence, you have really rapidly moving air. That really rapidly moving air means that according to the Bernoulli equation, what happened to the pressure? It goes down because the higher the speed, the lower the pressure. And so because of that low pressure, you have things pulled up by the tornado. Thermodynamics. Thermodynamics, we had 4 laws of thermodynamics. The first one is called the zeroth law. Why is it zeroth and not first?
Because they came up with it after.
Because they came with it after. It seems extremely obvious. Nobody thought you'd have to make this a law. You know, if 1 equals 1 and 1 equals 1, then 1 equals 1, right? If temperature A equals temperature B and temperature B equals temperature C, then temperature A equals temperature C. It's really obvious until you get to a more in-depth understanding of temperature, and all of a sudden it becomes not obvious. And so they said, oh, this is important, and it became the zeroth law. First law, energy can't be created or destroyed. We have our symbols here. U is internal energy. That's a Y. G. That's the kinetic energy of the molecules, the potential energy of the molecules, all put together. And then W is the work done by the system. And of course, I forgot and skipped Q. Q is equal to the heat added to the system. Heat is a transfer of energy. Work is a transfer of energy. How do you distinguish between 2 different transfers of energy? If there is work done, you have to have a motion. So in thermodynamics, that motion is a change in volume. So the work is pressure times change in volume. You have some motion involved. Heat is a transfer of energy without motion involved. Now, I say without motion involved. It has microscopic motion involved. My little molecules come and they hit your little molecules, and the collision transfers energy. That's how heat is transferring energy. But my little molecules were just going like this, and they hit, and then they slowed down. And his little molecules were just going slow, and then after they hit, they were going faster, and that's how heat got transferred. Okay, so those are the things in that equation. The second law has many statements, but one of the most important is that heat naturally flows from higher temperature to lower temperature. Really seems real obvious, right? Other statements are things like the entropy of the universe always naturally increases, or I like to say things naturally go to the lowest potential energy state available to them. That's not exactly correct. The real correct statement, I don't remember whose statement, is that you have energy equally spread out among all ways that it can be stored. That's what things are actually going for. And the third and final law, nothing can actually reach absolute zero, that there's an absolute zero temperature, a temperature where, in theory, you have reached minimum energy state possible. In a class like this, we usually say that means that motion has ceased. Well, the truth is motion doesn't cease at absolute zero because it's not possible, but absolute zero is the lowest possible energy state. It's quantum physics that says it's not possible for motion to cease. It's impossible for me to stop moving. It's a law of quantum mechanics. Unless I'm free to cover the entire universe, then I can stop. So we have those 4 laws, the 3 laws of thermodynamics plus the 0th law. So make sure you understand those. Thermal equilibrium. If 2 things are in thermal equilibrium, that means I bring them into thermal contact, touching each other, and no heat flows between them. Since heat always flows from hotter to colder, if things are in thermal equilibrium, I bring them together, no heat flows. What does that tell you about temperature? Has to be the same temperature. Calorimetry. Calorimetry is based on equations like this. Q equals mc delta T. where C was the specific heat of the material. Q is the heat, delta T is the change in temperature. So if I put a heat Q into something, its temperature change is calculated by this equation. And so if I take something hot and something cold and bring them into thermal contact, I'll have heat flow between them until they reach the same temperature, and I can use this to determine information about my system. I'll stop with this slide here since we are out of time. It's 10:20 right now. Make sure you know the three mechanisms for heat: conduction, convection, radiation. Remember the heat engines such as Tyler showed us for his demonstration. And yeah, then we have the recent stuff after that. There may be questions that were on time. I will be taking them from the same list of potential test questions and the same textbook questions.
So it could be questions we have.
The what?
There could be questions we have.
Yeah, there could be repeat questions. It won't be like half of them, but like I did use half of the questions available in potential test question, so there's a pretty good chance there of repeat questions, especially for the ones that you wrote.